अच्छा चले this is February March 2021. अच्छा चले this is so this one. We're going to try and solve this A2 chemistry past paper. Let me just set things up. February March 2021. उधर से start करते हैं. ठीक है, starting with the first question. This one over here is about transition metals. So we're going to try and do this. सबसे पहले तो वो कह रहे हैं कि cobalt, write down the electronic configuration of cobalt 2 plus and cobalt 3 plus. So I would have to open the data booklet now. So let me just open the data booklet and see कहाँ पे. अच्छा, so let's open the data booklet. Cobalt over here. If you can see cobalt, the cobalt is 27, and that's 27 electrons. So we're going to write the electronic configuration of cobalt. That is going to be 1s2, and then you're going to have 2s2, 2p6, 3s2. You've got 3p6. Then you've got 4s2, that's 20 electrons. Up at D, जो है ना वो when you're writing electronic configurations, so you're going to write a D at the end, which is going to be 3d7. Just confirm this one more time that is 27 electrons. Cobalt had 27 electrons. So this is what the electronic configuration is. But now you're looking at the electronic configuration of the cobalt 2 plus ions. That means 2 electrons are lost. So यहाँ पे ना the 2 electrons are always lost from the outermost shell. So it's going to be 4s0. And दूसरी side पे you've got cobalt 3 plus would be 3 electrons lost. So 1s2, 2s2, 2p6. And then you've got 3s2, and then you've got 3p6, and then you've got 3d7. 1 electron would be lost from 3d as well. So that's going to be 3d6. This one is an electrochemistry question. You're being asked, use data booklet in the table. You data in the table, this one. And you're being asked to predict what happens, if anything, when separate aqueous solutions of cobalt ions and cobalt are left to stand in the air. So cobalt 3 plus, if any, when separate aqueous solutions. So they're separate. So cobalt 3 plus with air. So what is air? Air is O2, obviously. So cobalt 3 plus with air. Remember, higher potential. Like look at cobalt 3 plus equations and look at the air equation, which has oxygen in it. So higher potential always gains electrons. It gets reduced. A lower potential, it loses electrons. So the higher potential is going to gain electrons, and the lower potential is the one that's going to lose electrons. So I don't think there's any specific reaction that's happening uh, with air specifically, because this is the lower potential. You just predict what happens. I'm going to write down the equation. What's going to happen is the electrons need to be balanced. So it's going to be 4, 4, and 4. The reason I'm multiplying it by 4 is 4 electrons gained and 4 electrons lost. So write down the reactants. That's 4 cobalt 3 plus ions. And over here, there's 2 water molecules. And the product that you're going to have is 4 cobalt plus 2 ions. And the other product is going to be O2 plus 4H plus 1. So again, based on what the data booklet is suggesting, I don't think there's any reaction that's happening. It's happening with water, but if anything, when separate aqueous solutions of cobalt are left to, it is an aqueous solution, so it will react with the water though. But let me just quickly refer to the marking scheme as well. This is M21, question paper 2-1. Just one. So, sorry, this is M21, question paper 4-2. M21. and 4-2. So apparently, my hunch is there's not going to be any reaction. At least not with air because it's not reacting with air. Oxygen has a lower potential, so it's going to lose electrons. It's not going to gain electrons. So and just 1 second, let me change this to. So the first one, they're actually giving you this equation actually. That the cobalt 3 plus ion is reduced to cobalt 2 plus and oxygen gas is evolved. It is produced. So the question is kind of misleading over here. If anything, when separate aqueous solutions of cobalt 3 plus ions are left to stand in the air. So what I'm assuming is that the cobalt 3 plus, since it's aqueous, cobalt 3 plus, if it's left to stand, it will react with water. So the reaction is not specifically with air, and oxygen gas is going to be evolved. So that part makes perfect sense. So I mean, this is what's going to happen, and use data to predict what would happen. Oxygen gas would be evolved. An aqueous solution of cobalt with eta, which is a bidentate, which is a polydentate ligand. Cobalt with EDTA. So what will happen when it? So I'm going to rub off all of that, and let's now see what would be the reaction in this case. So this over here, it's cobalt with EDTA, and that's the air, with 1.23 volts. So the higher potential always gains electrons. So that's going to gain electrons. It's going to go in the forward direction. And the lower potential, it is the lower potential, so it's going to lose electrons. So cobalt with EDTA is going to end up losing electrons. So now the problem over here is EDTA will not, cobalt with EDTA is not going to be able to react, simply because uh, it's got a lower potential. It can't gain electrons. It can't gain electrons. So this one over here, it can be produced, but it won't be able to react. Because for it to react, it should be part of the reactor. It's not part of the product. So uh, if I write the equations between the, it's being formed. It's not actually reacting with anyone else. So no change with cobalt with EDTA, not feasible. That is the reaction. So you can say the reaction is not feasible because if I अगर जबरदस्ती वाला काम करें, if I make this a reaction that I say that cobalt with EDTA gains electrons and the other one then loses electrons, the one with water or air that loses electrons, then this is going to be my reduction potential and that's going to be my oxidation potential. The E0 cell is reduction potential minus oxidation potential. That's 0.38 minus 1.23, and that comes out to be a negative value. That means it's not feasible. So the answer to this one is the reaction is not going to be feasible in this particular case. अच्छा फिर next one is hydrated cobalt nitrate .6H2 is a red solid that behaves like a magnesium nitrate. So when he says that, he's talking about magnesium nitrate. Describe in detail what you would observe when crystal of cobalt nitrate .6H2 are heated in a boiling tube gently at first and then more strongly. So the first part is when you're gently heating, the water of crystallization would uh, this .6H2O that is going to evaporate. It's going to be cobalt nitrate, and you'll see steam forming. That's the first part. And when you start to heat strongly, remember to write your words properly. I mean, it should be a proper strongly heating. I mean, you should write strongly heated. So when you write strongly heated, एक second में check कर लो. अच्छा, so when you write strongly heated, what happens is the cobalt nitrate that has been formed will eventually decompose and it will form cobalt oxide. Plus, it will form NO2, which is a brown gas, and will release oxygen gas molecules. So basically, we're writing an equation for magnesium nitrate. So the question is, what you would observe is not describe in detail what you would expect to observe. So it's not about writing equations, it's more about observations. So steam, first one, you're going to see water droplets, steam forming, and the second one is you're going to see brown gas forming. Uh, that's about it. That is what you're going to see. So I'm going to just check what the visual observations is. Condensation on tube or steam evolved. That's one. Brown fumes, that gets you your 2 marks. You can go and test for oxygen, but again, that's not really an observation because when oxygen gas is formed, you will not probably be able to see it. Uh, or solid dissolves to turns to liquid. Okay, I mean, it's assuming that the solid dissolves because I mean that's if there's water present. But the first two are the more reasonable assumptions. Now, explain why the thermal stability of group 2 nitrates increases down the group. So, why does it increase of group 2 nitrates? The reason is simple. The top one is a smaller ion, let's say it's plus 2. And you've got, he's talking about nitrate. So the nitrate ion is this one. But when you go down the group, the size of the ion, the charge is still plus 2, but the size of the ion is bigger. The top ion has more polarizing ability. So what it does is the plus 2, it's got smaller ions have more charge density. So since it's got more charge density, remember a charge that's concentrated over a very small ion is like really really strong. So it's going to attract the oxygen very strongly to it. And let's say that's magnesium. So magnesium will pull its plus 2. It's got a very strong plus 2 charge. So it's going to pull the oxygen. It's going to polarize the nitrate ion and take away the oxygens from it. And the nitrate from NO3, it will turn to NO2, and half oxygen gas would be produced. So the nitrate would decompose because of the strong polarizing power. So the answer that you're going to write is, first thing is down the group, the ionic or cationic radii increases. I mean, it's better to refer to it as cationic radius, which increases. So charge density of the ion decreases. Of our ion, it decreases. And when that decreases, there's less polarizing power. So the nitrate ion is more stable. So barium over here at the bottom is not going to be pulling the the nitrate ion, the oxygen from the nitrate ion to it. So ठीक है, just hold on 1 second, Abdullah. ठीक है, just wait 1 second. अच्छा, so coming back, कहाँ गया? अच्छा, now coming back to the question. Here's another question. It's difficult to determine the lattice energy of FeO experimentally. So what he does is use the data from the data booklet in this Born-Haber cycle to calculate the lattice energy of FeO in kilojoules per mole. So it's a big question. But the question is pretty simple. They've done everything for you. Where is but where are the values that are given? Some of the values are stated, others are not. So the first thing is you have to figure out lattice energy, right? So lattice energy, remember, Hess cycle is one path is equal to the other path. So that's your one path. What's the other path? It's go all the way here, then come back and reach this point. That's kind of your other path. So you have to kind of figure out the missing values over here. First thing, half oxygen gas turning into oxygen gas. That's one. This step over here. So what is that step? That is basically an oxygen double bond being broken and oxygen gas being produced, an oxygen atom being produced. That's enthalpy change of atomization, and you can find that value if you open the data booklet. And again, this value is now going to be given with the question. There's no separate data booklet. Go and have a look at the oxygen, double bond oxygen, homonuclear. So that's this one. It's 496. So O2 being broken down and it's being turned into an oxygen gas atom. So this part is going to be 496, and that's going to be divided by 2. Why? Because you're breaking half a molecule. That's it. Then you've got Fe getting ionized, Fe turning into Fe plus one in this step. It just lost an electron. So how does it lose an electron? The ionization energies are given over here for different elements. So Fe, it's over here. The first one is 762. So you're given so that's this one over here is the first ionization energy, and that is given as 762. So I've written that as well. Up here, next step is losing the second electron as well. So we have to, like, Fe plus one turns into Fe plus two. Nothing is happening to the oxygen over here. So it lost the second electron as well. So that's 1560. Remember, the ionization energies are given over here. That's first and the second. So Fe is going to be 1560, the second one. And the rest are provided. What else is missing? This is also given. This is also given. So only values missing were these three values. Those were the only values that are missing. So I'm going to take enthalpy, lattice energy. That's my path number one, and I'm going to make it equal to the path which is number two. So delta H lattice energy is going to be what? Remember, if you go in the opposite direction of the arrow, the sign has to change. So this is going to be minus 798. This one, again, I'm going in the opposite direction to the arrow. That's going to be plus 141. Then again, in the opposite direction of the arrow, that's minus 1560. Then again, opposite direction, traveling the other way, it's minus 762. Then again, going in the opposite direction, that's minus 496 divided by 2. Next one, still going in the opposite direction, that's 416, I guess. So that's minus 416. This one is the right direction, that's minus 272. So a lot of negative values, and that's it. I've reached my point. So I have to calculate all of this. I'll just look at the marking scheme and see what the answer. I mean, remember, you have to be very, very, Abdullah, you have to be very, very careful when you're doing these calculations on your calculator, because it's pretty very easy to make silly mistakes. So the answer to this one, it's the exact same expression, and hopefully that would give you minus 39. Hopefully it would give you minus 3915. So it's minus, this is minus, this is minus, minus. The only value that was plus was this one, and 798, that was also my minus. So everything is the same. So if you do the math, it should come out to be minus 39. It's going to come out to be minus 3915. Chale, let's move to the next one. It's a moles question. So the next one is, and hold on a second. As I said, the next one. E-question. You've got most naturally occurring samples of iron 2 oxide are found as the mineral wostite. Wostite has the formula Fe20OX. It contains both Fe2 plus and Fe3 plus ions. So that's 90% of the iron is present as Fe2 plus and 10% is present as Fe. Deduce the value of X. So So it's Fe 20 and OX. So the question is, he said he's already told you that 90% of the iron is present as Fe2 plus. So I've got 20 irons. What's 90% of that? What is 90% of 20? That's I guess that's 18. So that means I've got 18 irons which are in the form of Fe2 plus, right? So I've got 18 of them. And the rest of the 10%, what's 10%? That's two. You're left with two. Two of the irons in this formula are Fe3 plus. So two of them are Fe3 plus, just two of them. So that's your 90%, and that's your 10%. So I'm going to try and figure out the oxygen atoms now. So I basically broken down this formula over here, which is that I've got Fe2 plus. 90% of them are Fe2 plus. 10% of them are Fe3 plus. So I've just broken that down. That means I've got in the formula I've got 18 Fe2 plus ions, and I've got two of them as Fe3 plus. So I'm just going to try and figure out, like if I have Fe2 plus, so for every Fe2 plus, there's going to be one oxygen. Oxygen has -2 charge. So in the formula, it's going to be FeO if it's Fe2 plus, right? It's going to be FeO. On the other hand, I need two Fe3 plus ions as well. So if I have two Fe3 plus ions, the formula with oxygen, Fe3 with oxygen, if you do crisscross, it's going to come out to be Fe2O3. It's going to come out to be Fe2O3. So that contains two iron ions. And over here, I've got 18 FeOs. So I've got 18. The formula of Fe plus 2 with oxygen is FeO. So I've got 18 of them. 18 of my irons are in the form of FeO. Two of them are in the form of Fe3 plus. So they're going to make this formula. So what is the total number of oxygens? That's 18 over here and 3 over here. So the number of oxygens is going to be 21. So it's going to be this one is going to be Fe20 and O is going to be 21. That is what the formula is going to come out to be. इस case में. The next one is, so let's move to the next one, which is, where's the state explain why the lattice energy of FeO is compares to the lattice energy of now lattice being stronger depends. Here's your FeO lattice and here's your calcium oxide lattice. So the lattice energy depends on the strength of the ionic bond. So the strength of the lattice depends on two things. It depends on the charge density, it depends on the charge density. The bigger the charge, so it's directly proportional to charge, and it's going to be inversely proportional to the radius of the ion, the ionic radii. So it's going to be inversely proportional to it. Now, just hold on one second. So it's going to be inversely proportional to it. So what is happening here is that I've got Fe plus 2, O minus 2, and calcium. So the charge is kind of the same. So the charge is not really a factor because both ions have exactly the same charge. The bigger factor is the ionic radii. I need to open the data booklet. Fe plus 2 and calcium plus 2. The smaller the ion, the greater would be the charge density, the stronger would be the lattice. And smaller ions are more tightly packed together. They've got greater charge density. So there's somewhere where the size of the ions are listed. Somewhere, someplace, not really sure which place, but this one. So I've got, I'm going to code the two values. Calcium, that's hopefully group 2. Calcium over here, the ion is 0.099. So let's code that. Calcium has an ionic radius of 0.099 nanometers, I guess, whatever the unit is, nanometers. And let's look at iron. Not really sure where iron is. Fe, did they give Fe metallic? So is there Fe anywhere? Here's Fe. And he's talking about Fe plus 2, that's 0.061. So we're going to quote that. This is 0.061. So Fe is clearly the smaller one. So you're going to write that it has a greater charge density, Fe over here, and which is why it's going to have a stronger lattice. So that is the answer to this. It's just 2 marks. So you're going to explain it in that way. Now, the next part is heating FeO results in the formation of Fe3O4 as shown. Each unit of Fe3O4 contains Fe plus 2 and 2 Fe3 plus ions. Show how the reaction 1 can be described as disproportionation. It can be described as disproportionation because Fe goes from it's plus 2 over here and 0. So FeO plus 2, it turns to Fe, which has an oxidation state of 0. So it got reduced, or it gained electrons. And at the same time, Fe plus 2 in FeO went to Fe3O4, where he says that there are 2 Fe3 plus ions. So that means it got oxidized or lost electrons. So you're just going to write that. That's just 1 mark. And you're going to quote both these things. This is how, where's the answer? Fe plus 2 reduced to Fe, Fe2 plus oxidized to Fe3 plus. That's why disproportionation is the reaction where the same element gets oxidized and reduced at the same time. Now, the next one is write the half equation for the reaction that occurs at the anode during the electrolysis of Fe3O4 molten. It's a molten, so you don't have, I mean, the 2 ions. He's already told us that Fe3O4 contains Fe plus 2, and it also contains Fe plus 3. These are going to go to the cathode, so he's not really looking for the cathode reaction. They're going to get attracted to the negative electrode. They're looking at the anode. The anode would be the oxide ion, O minus 2 ion. That's going to go to the anode, where it's going to lose electrons to form oxygen gas. So that's going to be your reaction. Next one is calculate the maximum mass of iron metal formed when Fe3O4 is electrolyzed for 6 hours using a current of 50 amperes. Assuming that 1 Fe2 plus ions and 2 Fe3 plus ions are discharged at the same rate. Not really sure what that means. What I'm going to do first is I'm going to figure out the current and its time. So if you have time, 6 hours, 6 hours is how many seconds multiplied by 3600, because 1 hour contains 3600 seconds, and the current is 50 amperes. If you do the math, do the calculation, I'll just look at the marking scheme. If you do the calculation, it's going to come out to be this is what you're getting. It's 50. I mean, this one over here. So you're getting 1.08 into 10 to the power 6. You're getting 1.08 times 10 power 6 coulombs. Now, the next part is once you have coulombs, what you're going to do is charge and moles have a ratio, which is the Faraday constant. 96,500 coulombs is equal to 1 mole of electrons. So 1 mole of electrons have 96,500 coulombs charge on them. So if you have 1.08 into 10 to the power 6 coulombs, then what is the number of moles of electrons that would be flowing through the circuit? So you're going to crisscross and cross multiply. So X would come out to be 1.08 times 10 to the power 6, and it's going to be divided by 96,500. And this is must have been done somewhere over here. 1.08 divided by 96,500, and that comes out to be 11.19 moles. So you're getting 11.19 moles of electrons. Now the next part is you figure out the moles of electrons that are flowing through the circuit. So how do you figure out the moles of iron now? So I've got Fe2 plus, and I've got 2 Fe3 plus ions. Now Fe2 plus needs 2 electrons to form Fe, and Fe3 plus would need 6 electrons to form, because at cathode both ions would be gaining electrons, so it would need 6 electrons and to form 2 iron atoms. So the very first thing is, so what is happening here is, let's just add up this equation. So he's saying both reactions are happening together. So I'm going to add this up. So I've got Fe2 plus, and I've got two Fe3 plus, and together they're going to need 8 electrons, and they would form 3 Fe atoms. So my ratio, I'm only dependent on this ratio. It's 8:3. That you need 8 electrons to form 3 Fe. So if you have 11.19 moles, how many moles of iron would be produced? That's going to be if you use the ratio 8:3, it's going to be 11.19 divided by 8 multiplied by 3. So it's going to be 11.19 divided by 8, and it's going to be multiplied by 3. And that would be done somewhere in the question as well. 3 by 8 into M1, which gives you 4.2 moles. And they also wrote the same equation. So that gives you 4.20 moles. So I figured out the moles of iron that are getting produced. So the moles of Fe is, if you do the math over here, it's going to come out to be 4.2 moles. And the last part is you multiply it by the MR to find the mass. Mass would be the MR into the moles of Fe. Make sure write these small statements when you're doing a moles question, because that's very important. Uh, because if you look at the marking scheme, they're going to look for clarity. The examiner would want to distribute the marks. So if you just make one messed up calculation and assume that the examiner is going to know what is happening, that's not going to work. So make sure write small statements explaining what you're doing. For example, if you use Q is equal to IT, explicitly state that you're using that. Just don't randomly or quickly in a hurry just write the answer, whatever the answer is. ठीक है, Abdullah. So they're looking for it's the last part. We have to multiply it by the MR of Fe, AR of Fe, which is 55.8 in the booklet, and that would give me 234.2 grams. And that's going to be my answer. And that's I guess about it. And the minimum three significant figure. They're looking for 3 significant figures minimum accuracy. So the next part of the question. It's 1 second, Abdullah. So the next part of the question is you've got this one. I don't know what this is. Can be used in a lithium-ion rechargeable battery. When the cell is charging, lithium reacts with the graphite electrode to form LiC6. When the cell is discharging, the half equations for the two processes that occur are as follows. State one possible advantage of developing cells such as rechargeable battery. There's less dependence on what's but it's very low mass, high voltage. ठीक है. Compact, low mass, high voltage. Lithium ion, when the cell is recharging, reacts with to form. ठीक है. They've stated one possible developing cells such as. ठीक है. They basically said that it's more compact. I mean, lithium batteries are more compact. You use them in your phones and your electronic devices. So you want batteries that are more. I mean, a lead acid battery is a pretty big battery. So you like car batteries. So lithium ion rechargeable batteries are more compact. Use the cathode half equation to determine the change, if any, in oxidation states of lithium and iron at the cathode during discharging. So what's happening to lithium over here? And he's saying the change in oxidation state during discharging. So lithium and iron, and this is when the cell is charging. Lithium reacts with a graphite electrode to form Li6 C6 when it is charging, and these are the equations for discharging. So lithium over here, what is the oxidation state of lithium over here? This is +1, and over here it's going to be, it's gaining 1 electron. So So the change in oxidation number, and what is what is lithium over here? Lithium with C6. ठीक है, दोनों cases में we have to figure out what the change in iron as well is. Iron is definitely +3 over here because PO4 is -3. So PO4 is -3. If it's a neutral molecule, iron must be +3. And over here, iron is going to be, if PO4 is -3, lithium is group 1, it's going to be +1. So lithium is group 1, it's going to be +1. Iron would therefore have to be +2 because the overall charge is 0. And also remember, uh, someone is gaining electrons. It's not lithium, it's iron that goes from +3 to +2. So iron is going from +3 to +2. Now in the first one, someone is losing electrons. So who's losing electrons? It's definitely not carbon because it's not forming a positive ion. Lithium must be forming the positive ion. So lithium will have an oxidation state of 0 over here. 0, then it lost electron, one of them, and it would form +1. Write the equation for the overall reaction that occurs when this cell is discharging. So discharging, you just add up the two equations. But so you add up the two equations. So it's going to be LiC6 plus Li plus 1, I guess. And you add up the left-hand equations, it's FePO4 plus electron, that's all on the left-hand side. And on the right-hand side, you have 6 carbons. You've got an Li, which is +1. And you've got LiFePO4. So LiFe and PO4. You're going to remove the terms which are common, and there's one electron being produced on the right side, so the electrons are going to get cancelled out, and the Li plus 1 is also going to get cancelled out. So your leftover equation is going to be LiC6 plus FePO4, and it forms 6C plus LiFePO4. That's going to be your overall equation. So make sure when you add up two equations, you have to make sure the electrons are equal. You add the left hand side and you add the products, and cancel anything that is common on both sides. So that is what you are going to do in this case. So moving on, next one, write the equation. We've done that. There's an IO3. Explain with reference to the qualitative model of electron pair why the IO3-1 ion has a pyramidal shape. According to the qualitative model, which is iodine is in group 7. It's got 7 valence electrons. So 2 electrons shared here, 2 electrons shared here, 1 shared. That's 5 electrons. Like if you have 5 bonds, that's 5 electrons being shared. So that means there's definitely a lone pair. There are 2 electrons that are left. So this molecule would actually be like a pyramid. Oxygen double bond oxygen. There's going to be another oxygen double bond oxygen, and there's going to be one with the O-1, and there's going to be a lone pair that would be sitting on the top. So it's got one lone pair, and it's got 3 bond pairs. So it's going to be trigonal bipyramidal. It's just one mark. So not really sure. They're just going to look for if I look at the marking scheme for this one, you just have to state that 3 bonding pair centers and 1 lone pair. That's it. The reaction of iodine and hot aqueous sodium hydroxide is similar to that of chlorine and hot aqueous sodium hydroxide. Sodium iodide is formed as one of the suggested equation for the reaction of iodine with hot aqueous. So the reaction of iodine with hot aqueous NaOH. So iodine with hot aqueous NaOH is similar to that of chlorine with hot aqueous NaOH. So what happened with chlorine? It would form NaCl. Now it's going to form NaI. It would form NaClO3. In this case, it's going to be NaIO3, and it's going to form water. And this is something that you have to memorize in group 17, and you also have to memorize it's better to just memorize the balancing of the equation as well, because balancing this equation, it's a redox equation, so it's pretty hard to balance the number of electrons that are gained and that are lost. So moving on, the decomposition of the hydrogen peroxide is catalyzed by acidified IO3 minus 1. And it says that H2O3 reduces acidified IO3 minus 1 as shown. The reaction is followed by oxidation of I2 by H2O2. So H2O2 reduces IO3 minus 1. This is the first reaction. And then he says the reaction is followed by I2 by the oxidation of I2 by H2O2. So use data to show that the separate reaction of H2O2 with IO3 minus 1 and I2 are both feasible under standard conditions. And in your answer, so the first one, let's talk about this one. Is it feasible or not? So you can see IO3 minus 1 turning into I2. So I've got IO3 minus 1 and it's turning into I2. That's my reduction equation. That's the one that's gaining electrons, right? And I've got H2O2 turning into O2. So where's H2O2 turning into O2? So it's this one. So higher potential gains electrons. That's my reduction potential. And lower potential loses electrons. So this is my oxidation potential. So what I'm going to write is I'm going to code these two values for the first one. Why is this feasible? I'm going to code these values. I'm going to calculate the E naught cell for this. So this reaction is made up of these two equations. This gaining electrons, this losing electrons. And how do you calculate the potential difference? It's the reduction E naught minus the oxidation E naught. So minus the oxidation E naught. So it's going to be 1.19 minus 0.68, and it's going to give me a positive value. So that's why when you get an E naught cell which is greater than 0 or positive, it's something positive. I mean, we can look at the data booklet and see the math over here. Something that's positive, 1.19 minus 0.68, that gives you 0.51. So we're getting 0.51 for this, which is a positive potential. That's the first one. Then he says the other one, which is, and let's try and solve the other one. The other one, he didn't give the equation. He just said that followed by the oxidation of I2. So oxidation of I2 means this losing electrons by H2O2. So H2O2 must be gaining electrons, this one. So by the oxidation of I2, I2 losing electrons, H2O2 gaining electrons. Who gains electrons? The higher potential. This is the reduction potential. Who loses electrons? The one that has a lower potential. So, and he's also asking to give the equation for the reaction. So we're going to give the equation. All I have to do is I have to sort of add the two equations up. And okay. Achha, all I need to do is I need to add the two equations up. But before that, I would need to multiply the bottom equation by 2 and the top equation by 5, because I need to make the number of electrons gained and lost. They got to be equal. And add up the reactants. The first one, the reactant is 5H2O2 and 10H plus 1. I mean, that's my reactant in the first one. And the second one, the reactant is, it's being multiplied by 2, so it's going to be I2 plus 6H2O. And then I'm going to write my products. The first one, the product that is being produced is 10 H2Os. Okay, second one, the product that's being produced is 2IO3 minus 1 and 12H plus 1. And that's about it. The electrons are going to get cancelled out. And I'm going to write the E naught cell. Why is this feasible? Reduction potential minus oxidation potential. It's going to be 1.77 minus 1.19. And if you do the maths, which I'm not going to do, I'm just going to 1.77 minus 1, but that's going to give me 0.58. So that gives me 0.58 voltage, which is again positive. So you're going to write specifically, right? You're getting a positive value, so this reaction is feasible. And make sure when you get this equation, cancel out anything that gets cancelled out. So instead of 12H plus 1, there's going to be 2H plus 1 on this side. And the 6 water molecules are going to get cancelled out as well. Instead of 6 water molecules, there's just going to be, cancel it like a math equation. Like 6 water molecule, take them to the other side. That's going to be 10 minus 6 water molecules. अच्छा आगे चलते हैं. We've got Write the whole equation for the decomposition of H2O2 catalyzed by IO3 minus 1. So you have two reactions. One is 5H2O plus, and I think this is 5H2O2 plus I2, and the product is 4H2O plus 2IO3 minus 1 plus 2. I mean, I'm just copying the equation over here. This one. So that's one reaction. And let me just double check this. Is this the equation? We're getting the same equation. And what's the other one? The other one was the first one. It's 5H2O2 plus 2H plus 1. So this one is 5H2O2 plus 2H plus 1 plus, I mean, I'm writing this equation over here, 2IO3 minus 1. And the product is I2 plus 5O2 plus 6 H2Os. And what we're going to do is we're going to just add up the two equations. The two H plus ones are going to get cancelled out. The two IO3 minus ones, they are going to get cancelled out. The I2s on both sides are going to get cancelled out. So you're left with 10 H2O2s on one side, and on the other side I've got 10 H2Os, and I've got 5 O2 gas molecules. That's my product side. So the two reactions that I had, I just added them up. I got this equation, which can be further simplified. You don't need 10 H2O2s. It's just going to be 2 H2O2s, and it would form 2 H2Os. Remember, equations are better. They better be in the simplest form. So that's it. So now, the next one. It's about this one is about orders of reaction. So you have to find the order with respect to H2O2. So what I'm going to do is I'm going to look for equations or look for reactions uh, where only H2O2 is changing. So I'm going to compare experiments 3 with experiment number 4, uh, because remember that's my variable, and I'm going to see how the rate changes with my variable. The other everything else has to be kept constant. So in experiment 3 and 4, this is kept constant. Now, what you're going to do is you're going to find the change, the percentage change, or the ratio in which it changes. So the way you find that out is 0.15. Take 0.15 divided by zero point 0.1. Let me just open a simple calculator. Okay, not sure if you can see this. So what I'm going to do is 0.15 divided by 0.15 or 0.10. 0.15 is going to be divided by 0.1. And that gives, I mean, that was pretty obvious. It was one, it's a change of 1.5 times, 1.5x. And I'm going to see how the rate changes. Now I've got, this is 10 power minus 5, 5.88 times 10 power minus 5. It changes to 8.82 times 10 power minus 5. So I'm going to use my calculator to find that it's going to be 8.82. I'm going to figure out the factor, which is what's the factor wise change? 8.82 divided by 5.88. And that's also 1.5 times. I mean, this one over here is also coming out to be 1.5x. So this is clearly order is 1. It's order 1 means it's directly proportional. That means that the rate is directly proportional to the concentration of H2O2, and the power is 1. So directly proportional. So the ratio in which you change this, the same ratio, the rate would also change. So it's going to be. So what you're going to write is, if you compare, you're going to write specifically, tell them which experiments you're comparing. So if you compare experiments 3 and experiment number 4, so the concentration of H2O2, you're going to write that the concentration of H2O2 changes by 1.5 times, and your rate also, it ends up changing or changes 1.5 times. So that's how you're going to figure out order of with respect to H2O2. Next one is IO3 minus 1. So we have to figure out the order. So I'm going to rub all of this, and I'm going to try and find the order with respect to. So I'm going to try and find the order with respect to IO3 minus 1. उसके लिए क्या करना है? तो ये वाला है, it's ऊपर लिखा है, it's M21 question paper 4.2, I guess. चलिए, Abdullah. Let's move to the next one, which is IO3 minus 1. So I want to figure out how IO3 minus 1 and the rate are linked up. So I want to keep all the other things constant. So which experiments do I compare? Now over here, I think we are going to have a problem, which is what? Which is like if I compare this with this, or no, I can actually compare experiments 2 and 3. There's no problem. H2O2 is constant. No, sorry, that is changing. So that's a problem. We can't. I mean, only one of the variable has to change. Uh, what I can also do is if I compare 1 and 2, I mean the IO3 minus 1 should vary. So that can't be done. 3 and 4 can't be compared. The first one, I mean, the second one can be compared with, but every time this would change. The first one can be compared, but this would still change. So every time everything is changing. So what's the other way of finding the order? Now we're going to do the longer mathematical way, which is that I have a rate equation. The rate equation is, I mean, the rate equation at the moment is incomplete. I don't know what the rate equation is, but I know some of it partially. I know that the rate is equal to, there's a constant, it's proportional to, if you remove the proportionality, there's going to be a rate constant. And it's equal to the concentration of H2O2. For H2O2, I've already figured out what the order is. It's 1. For IO3 minus 1, I don't know what the order is. For H plus 1, I don't know what the order is. So I'm going to call that A, and I'm going to call this B. And what I'm going to do is I'm going to plug in experiment 1 and 3 values into this. The reason I want H plus 1 to be kept constant as well. So I don't want H plus 1 to interfere in the experiment. Can't really help with H2O2, but for H2O2, I already know the order. So I'm going to plug in the values of the first experiment into this. If I do that, the rate is 1.47 times 10 power minus 5. So it's 1.47 times 10 power minus 5. I've got K over here. The H2O2 concentration is given as 0.05 in the first experiment. So remember, this is experiment 1. So it's 0.05. And the power is 1. I already know that. I've already calculated it in the previous experiment. So that's already been done. Acha, IO3 minus 1. I've got IO3 minus 1, and that is 0.07. And for that, I don't know what the power is. So let's call that A. And H plus 1 is 0.025. I don't know what the order is. So it's 0.025. And that's B. Now, using experiment 1, what I'm going to do is I'm going to write an expression for K. Remember, K is a constant. So K is 1.47 times 10 power minus 5. And K basically has to be divided by 0.05, power 1, 0.07, that's power A, and 0.025, that's power B. So that is my constant. That's my constant value. I'm going to use experiment 2 now. I'm going to plug in the values of experiment 2 into the same rate equation over here. So when I do that, let's do experiment 2. So when I do that, the rate is 5.88 times 10 power minus 5. And my concentration for H2O2 is coming out to be 0.1, and that's power 1. And there's a K as well. Again, there's the same K. So we need so so that K goes over here. So rate the same equation. H2O2, that's 0.1, power 1. The other one is 0.14. That's the power that I don't know, so I'm going to call that A. And H2O2 is still 0.025, and that's power B. So I've gotten this expression. So I've got my two expressions. Experiment 2 and experiment 1 values were actually plugged in. So let's go with experiment 2 now. So I'm going to take this K and I'm going to put it over here. So that requires a bit of a math. It's five. It's simple math, but 1.88 times 10 power minus 5. I'm going to plug in the K value over here. The K value is 1.47 times 10 power minus 5, and divide by this whole thing, which is 0.05 and 0.07 A and 0.025 B. And the top over here is 0.1 into so this one is 0.1 into 0.14 A and into 0.025 B. So the 0.025 B gets cancelled out. So all that is left is 0.14. So all I need to do now is I need to rewrite this expression. This is if I rewrite this expression, it's going to be 5.88 times 10 power minus 5, and that's going to be divided by, take this to the other side, though that's 1.47 times 10 power minus 5, and then there is zero point 0.1. So the 0.1 comes at the bottom, and the 0.05 goes in the numerator over here. And on the other side, I'm going to keep A to the other side. So it's going to be 0.14 over 0.07, and both of them have power A. So it's power A whole thing. So let's talk about this one. 10 power minus 5 gets cancelled out. So it's 5.88 divided by 1.47. So what is that? 5.88 divided by 1.47. And that gives me 4. That is 4 into, what is 0.05 divided by 1? That's probably half. But just to be sure, that is half. 0.05 divided by what? Divided by 0.1. So divided by 0.1. That's 0.5. And this over here is what is 0.14? What is 0.14 into divided by 0.07? That's going to be 0.2 power A. But just to be careful, 0.14 divided by 0.07, let me do that. 0.14 divided by 0.07. 0.14 divided by 0.07. That's actually 2, sorry. So I was wrong. So this one over here is actually 2 to the power A. And if you solve further, this is basically 4 into 0.5 is 2. It's equal to 2 to the power A, and A would therefore be equal to 1, because that's the only way this relationship over here gets satisfied. So that's a long, tedious method of solving this. This is the mathematical way of doing this. But remember, it's just a 1-mark question. You don't have to do all of this. So there's probably a shortcut, and that shortcut is you could have done this by just looking at experiment 1 and 3. You could have, I mean, it would be very hard, but you could have done that. What we did was we wrote a rate equation. We knew that rate depended on H2O2, that was order 1. We knew that. We didn't know what the orders of A and B were. I didn't know what H plus 1, the order with respect to H plus 1 was. So what we did was, okay, we used that half equation with these unknowns and we plugged in the values for experiment number 1. I tried to keep H plus 1 constant so that it gets cancelled out, because I want the order with respect to A. So I kept H plus 1 constant. I chose those experiments where H plus 1 was constant so that it eventually gets cancelled out. I did experiment three values into this, put those values over here. I took the K from the first expression and then put it over here. And then I simplified. When I simplified, I eventually got A is equal to 1. So that's how you figure out the order. If you can't find, that's the way you figure out the order. If you can't find two experiments where the powers are uh, getting cancelled out. Uh, Now the other thing is, how do you figure out uh, the order which is with respect to H plus 1 over here. So the way you're going to figure this out is that is kind of easy. I mean, for that, I mean, you can do the same math, but let's try and check experiment 1 and 2. So IO3 is not playing a part because it's constant. So this thing doubles, right? And the concentration of H2O2 also doubles. What happens to the rate? 1.47 becomes 2.94. That also doubles. But we knew that H2O2 is order 1. So order 1 means that if this doubles, this doubles. So that relationship, we already know that H2O2 is order 1. So the rate should double. So what is the effect of this other doubling that's happening? There is no effect. I mean, we know that this is getting doubled. Why? Because H2O2 is order 1 and that is getting doubled. We already know that H2O2 is order 1. So that means this other doubling that's happening, when you're doubling the concentration of H plus 1, that's not doing anything. Absolutely nothing is happening here. So that must be order 0. So I mean, that's how, by just looking at, you don't have to do the math every time, but the fallback is you do the math. So first order, and 0 order. So it has no effect on the rate of the reaction. Uh, so that's about it. अच्छा चले इसको कंप्लीट कर लेते हैं. We figured out the orders, so rate equation would be K H2O2. That was 1. और क्या था? The other one was IOC minus 1. That also came out to be 1. And then you had H plus 1, and that was 0. So basically, you don't even write H plus 1. But just to be on the safe side, write H plus 1. And calculate the value of the rate constant using data from the experiment. Give the units of K. So pretty much every time you get this question as well. So use the units that are quoted in the table over here. That's mole per dm cube per second. The concentration is mole per dm. Sometimes they use different units because remember the rate of the reaction is any change with respect to time. So it could be grams per second. It could be pressure changing per second. So usually it's mole per dm cube per second, but make sure use the units that are quoted in the question. So we're gonna find the unit over here. It's gonna be K. So this is mole per dm cube per second. I'm going to take mole per dm cube as X, mole per dm cube per second, and it's going to be divided by H2O2 mole per dm cube into IO3 minus 1. That's mole per dm cube into H plus 1. That's 0. So that gets cancelled out. I mean, you don't need H plus 1. So it's X minus 1, S minus 1. If you simplify it, so it's mole per dm cube to the power minus 1. So mole dm3 and S minus 1. That's your unit, and you can figure the value of K. I mean, just plug in the values from this experiment number 4 into this, and you find what K is. That's about it. That's easy. So this one is about KSP, saying it's only sparingly soluble in water at 25. The solubility of KSP at PBI through is 3.69. Write an expression for the solubility product of PbIO3 twice. So whenever an ionic compound dissolves, its ions, they dissociate, they scatter in water. So in a saturated solution, there's going to be a reversible reaction, and these would be your aqueous ions, and that's your solid. So इसका वो लिखते हैं solubility product, that's going to be product concentration. It's going to be PB plus 2 concentration into IO3 minus 1 concentration, and that's going to be squared. You don't write solid in the expression. It's got a constant. Now calculate the solubility in mole per dmq. So you don't know what the solubility is. I don't know how much of PBI through IO3 twice is getting dissolved. So let's call that x mole per dm cube. So if it dissolves, it's going to produce x moles of this and 2x moles of this. So mole per dm cube, and this would be x moles per dm cube as well. So I'm going to plug in these values. The KSP value is already given to me. It's 3.69 times 10 power minus 13. And the expression is over here. So it's lead ion concentration is x. And IO3 minus 1 concentration is 2x. And that's going to be squared. And if you simplify, that's going to be 4x cubed. So take the 4 to the other side and then take the cube root. It's going to be, you're going to take the cube root, so the 3 gets cancelled out as well, and that's going to be your expression for this. So the answer to that one is it's the same thing. They've done the same thing. It's cube root 3.69 into 10 to the power minus 13, and that's going to be divided by 4. Okay, the next part is use the data to calculate the entropy change for the reaction. Remember, delta S is the change in entropy. It's the change in entropy, the entropy of the products, minus the entropy of the reactants. We're not doing standard entropies over here. They didn't write not over here, so we're just going to use the same values. Just get rid of the not. So the product entropies are minus. What are your product entropies? That's the entropy of N2. That's 192 into half. That's the first one, half O2. That's 205 into half. Then you've got half I2, which is this one. It's 261. And then you've got 2 H2Os. That's 17 into 2. So that's your product, and you're going to minus your entropies of your reactants, which is, there's only one of them, so that's 42. So you're going to subtract 42 from it, and that will give you your answer, which is this one, minus 42. That's 427. So you're getting plus 427 for this. To explain, the reaction is feasible at all temperatures. Explain by using the data in your answer to F1. So data, what's the data? It's the enthalpy change is given. So when it's feasible, that means Gibbs free energy is always, it's the overall energy available to do useful work. That's always exothermic. It's always negative. I mean, less than 0, it means it's always exothermic. So the system is always producing work done. So how do you calculate delta G? It's the energy that is produced due to enthalpy change minus the work that is produced due to entropy change. So delta H is given, and that has a value of minus 154.6. And minus T delta S. Delta S is given as 427. So that's given as 427. So both your terms are negative. So you're going to write both terms are coming out to be negative. Delta H is negative, and minus T delta S also comes out to be a negative value. So which is why it's always feasible. It's always delta G is going to come out to be less than 0. There's no possibility of it coming out to be a positive value. So that's what will happen in this particular case. So question number 4. We'll stop here. ठीक है. We'll stop at question number 4. तो अब्दुल्ला ये फिर हम कल कंटिन्यू करते हैं, ठीक है? And let's continue tomorrow at the same time.